Is the night sky an honest map, or the most profound illusion ever witnessed? Every point of light you see, every constellation we have ever named, appears to be painted on the same distant black canvas. They feel close, equidistant, a comforting dome over our world. But this perception is a trick of biology and distance, a failure of intuition woven into our very DNA. Our minds, evolved to gauge the trajectory of a thrown spear or the distance to a far-off mountain, simply have no framework for the truth of the cosmos. The reality is a terrifying, exhilarating abyss of depth, where the space between the lights is a void so vast it defies all human metrics. For millennia, we have tried to conquer this illusion. We built astrolabes and sextants, trying to pin down the heavens with geometry. We invented the telescope, a tool to magnify the impossibly far, only to discover that the abyss was deeper than we could have ever dreamed. Each new discovery, each new order of magnitude we unveiled, did not make the universe smaller or more manageable. It did the opposite. It revealed an arena of such staggering proportions that our units of measure, our miles and kilometers, became meaningless whispers in a hurricane of scale. They are the measurements of a single grain of sand applied to a desert that stretches beyond any horizon. We are cartographers standing at the shore of an infinite ocean, and our journey to map it begins by leaving everything we know behind. Let us begin that journey now, pull away from the familiar blues and whites of Earth, the only home we have ever known. Watch as continents and oceans resolve into a swirling marble, then shrink to a delicate blue pearl suspended in an impossible blackness. Already, our sense of place is undone. The ground is gone. Up and down have lost their meaning. There is only the sun, a searing, unfiltered furnace to one side and the endless void on the other. Our first port of call is the moon, a silent, pockmarked world that for all of human history represented the very limit of aspiration. From here, our home is a brilliant blue star in the sky, a beacon of life in a desolate solar neighbourhood. But we are only just beginning. We push outward, past the red, dusty plains of Mars, a world that might have been a sibling to our own but suffered a different, colder fate. We feel the pull of the system's true heavyweight, the colossal gas giant Jupiter, a world so massive it is less a planet and more of a failed sun. Its great red spot is a perpetual storm wider than our entire planet, a hurricane that has raged for centuries, a testament to the violent physics that govern these larger worlds. This is a king robed in atmospheric rivers of ammonia and hydrogen, its faint ring system a subtle crown, its legion of moons a royal court of ice and rock. The scale shifts again. The distance from Earth to Jupiter, a journey that takes our fastest probes years to complete, becomes a mere stepping stone. Outward we fly, toward the jewel of the solar system, Saturn. Its rings, which appear so solid from Earth, resolve into what they are: trillions of pieces of ice and dust, the ghost of a shattered moon, arranged by gravity into a structure of impossible grace and fragility. Each particle, from the size of a snowflake to the size of a house, dutifully orbits the great planet in a cosmic ballet of sublime precision. We pass the tilted, pale blue sphere of Uranus and the deep azure of Neptune, where winds scream at supersonic speeds in an atmosphere of frozen methane. These are the ice giants, the lonely sentinels of the outer dark, worlds so far from the sun that its light is little more than a brilliant star. We are now billions of kilometers from where we started, but in the grand scheme of things, we have barely left our front door. We press on, past the Kuiper Belt, a scattered junkyard of icy debris left over from the formation of the solar system, and then we cross an invisible boundary, a place where the solar wind, the stream of charged particles flowing from our sun, finally collides with the interstellar medium. This is the heliopause, the true edge of our solar system. The sun's gravitational influence continues, but its atmospheric bubble has burst. We are now in the space between the stars. The distances here are no longer measured in the familiar language of travel. They are measured in the speed of light itself, the universe's absolute speed limit. A single light year, the distance light travels in 1 year, is nearly 10 trillion kilometers. It is a number so large that it is, for all intents and purposes, just a placeholder for unimaginably far. Our closest stellar neighbour, Proxima Centauri, is over 4 light-years away. To journey there, even in our imagination, is to experience a new kind of solitude. For years, decades, centuries, you would travel through a near-perfect vacuum, a darkness punctuated only by the distant, unwavering light of stars that never seem to get any closer. The emptiness is the story here. The universe, we are now beginning to truly understand, is defined not by its matter, but by the sheer, overwhelming scale of its nothingness. But we are not adrift. We are part of a structure, an immense celestial island. As we pull our perspective back further, the scattered lights of individual stars begin to coalesce. They merge into a luminous river, a glowing band of light that has haunted our skies and our myths since the dawn of consciousness. We are seeing our home, the Milky Way galaxy, from the inside. This is our city of stars, a sprawling, spiral metropolis of at least 200 billion suns, each one a potential anchor for its own system of worlds. Our sun is just one citizen among this countless host, residing in a quiet suburban spiral arm far from the chaotic city centre. Let us journey there now, toward the galactic core. The star fields grow denser. The blackness of space is replaced by a celestial fog, a brilliant haze of countless suns packed closer and closer together. The environment becomes more violent. We pass by pulsars, the collapsed corpses of massive stars, spinning hundreds of times a second and sweeping beams of radiation through space like cosmic lighthouses. We see stellar nurseries, vast clouds of gas and dust glowing with the ultraviolet light of newborn, blue-white stars that live fast and die young. We navigate through the gravitational fields of black holes, tears in the fabric of space-time, their presence betrayed only by the distorted light of the stars behind them. And at the very heart of it all lies Sagittarius A, the supermassive black hole around which our entire galaxy revolves. This gravitational monster, 4 million times the mass of our Sun, is a slumbering beast, a dark monarch holding our entire star city in its inexorable grip. We have now travelled 26,000 light-years from Earth. Our Sun is completely lost in the stellar glare, an anonymous speck in an ocean of light. Here, in the crowded, ancient heart of the galaxy, the stars are older, different. But we are not searching for the old, or even the strange. We are hunting for a true monster, a titan, an entity that pushes the very laws of physics to their absolute breaking point. To find it, we must leave the galactic core and travel to one of the galaxy's most active and crowded thoroughfares, the Scutum-Crux arm. This is a region choked with interstellar dust, a cosmic fog that makes seeing anything clearly a profound challenge. It is a place of giants, a stellar maternity ward where the most massive stars in the galaxy are born from collapsing clouds of hydrogen. Tucked away inside this dusty arm is a small, unassuming, open cluster of stars, catalogued in 1987 by the astronomer Charles Stephenson. He was surveying the sky using photographic plates, and in this particular region, he noted a collection of peculiar, extremely red stars. The cluster was named Stephenson 2. For years, it remained a point of interest for specialists but was largely obscure. The dust was simply too thick, our instruments not yet sensitive enough to pierce the veil. But as technology improved, as we developed new ways to see through the haze using infrared light, astronomers returned their gaze to this cluster. They were conducting a census of giants, and they began to realize that Stephenson 2 was not just a simple cluster. It was a cosmic royal court, home to an astonishing number of red supergiants, stars that were already unimaginably large. They analyzed the light from these stars, painstakingly measuring their temperature, their brightness, and their distance from Earth, which they calculated to be nearly 20,000 light-years away. And as the data for one of these stars was processed, a number emerged from the calculations that seemed impossible, a mistake. They checked their models, recalibrated their instruments, and ran the numbers again. The result was the same. Tucked away in this cluster, obscured by curtains of galactic dust, was a star so gargantuan, so mind-bogglingly immense, it shattered every existing record. It did not have a grand mythological name. It had only the sterile scientific designation given to it by the survey, Stephenson 2-18. Here, At last, our journey ends in the presence of a true Leviathan. For a long time, the title of largest known star was held by UY Scuti, another red hypergiant that was itself a celestial monster of unbelievable proportions. UY Scuti was the benchmark, the object we pointed to when we wanted to illustrate the upper limits of stellar size. But Stephenson 218 has dethroned the king. It is not just a little larger, its size represents a quantum leap in immensity, a challenge to our understanding of how stars can even exist. So how big is it? Let's try for a moment to wrap our minds around the scale of this object. Forget our Sun. Comparing Stephenson 218 to our Sun is like comparing Mount Everest to a single bacterium. It is a comparison that fails to convey any meaning. Instead, let us perform a thought experiment. Imagine we could replace our Sun with this star. The centre of Stephenson 218 sits where the centre of our Sun is now. The inner planets, Mercury, Venus, Earth, Mars, would not just be burned to a crisp. They would be gone, vaporized. They would be deep inside the star's photosphere, its visible surface. Our home, our entire history, would be nothing more than an insignificant puff of plasma swallowed by a thermonuclear sea thousands of degrees hot. We push further out. The asteroid belt vanishes. The colossal planet Jupiter, the failed star that dominates our own system, would be consumed without a trace. Its immense gravitational field would be a mere pittance against the star's own. We keep going, across hundreds of millions of kilometers of incandescent gas. Finally, we reach the orbit of Saturn, the ringed jewel nearly 1 billion miles from our Sun. Only here, just past the orbit of this distant giant, would you finally breach the surface of Stephenson 218. Every planet, every moon, every asteroid we have ever known in our solar system, with the exception of the distant ice giants, would be comfortably nestled deep within the volume of this single star. If you were to fly a spaceship at the speed of light, it would take you over 8 hours to circle its circumference once. A beam of light, the fastest thing in the universe, would take longer to cross this star than it takes to travel from the Sun to Jupiter. Its volume is so vast that you could fit nearly 10 billion of our suns inside it. All the awe and power we feel when we look at our own star, the engine of our world, is dwarfed into utter insignificance. UY Scuti, the former champion, now seems almost reasonable by comparison. This new king is a celestial entity, existing on a scale that feels more mythological than astronomical. It is a bubble of plasma stretched to the absolute breaking point, a seething, turbulent ball of fire so large that its own gravity can barely hold it together. It shines with the light of nearly 500,000 suns, a celestial blowtorch of unimaginable power, yet its outer layers are so diffuse they are more like a red-hot vacuum than the substance of a star. And so, we are left with the most profound question of all. A question that this entire journey has been designed to ask. How? How is this possible? How can a single, coherent object in our universe grow to such a terrifying and seemingly unstable size? What forces of nature conspire to build such a monster, and what prevents it from simply tearing itself apart under the strain of its own light and fury? This is not just a question of records or cosmic tourism. The existence of Stephenson 218 is a direct challenge to the laws of physics as we understand them. It sits at the very edge of the Eddington limit, the theoretical boundary where the outward pressure of a star's radiation becomes so powerful it should overwhelm the inward pull of its gravity, blowing the star to pieces. This star is an outlier, a freak, a beautiful anomaly that forces us to re-examine our most fundamental theories of stellar birth, life, and death. To understand this star is to understand the extremes of the cosmos. In our quest to solve this puzzle, we must become cosmic detectives, piecing together clues from faint light that has travelled for 20 millennia to reach us. We must invent new ways to measure the unmeasurable and to see the invisible. The story of Stephenson 218 is not just the story of a very big star. It is the story of our own relentless drive to map the void, to understand the monsters that live in the deep, and ultimately to find our own place in this impossibly large universe. For nearly all of human history, the stars were a beautiful deception. Pinned to the celestial vault, they appeared as a spray of cold, unchanging diamonds, equal in stature, their true natures veiled by an abyss so profound it defied imagination. We saw them not as they were, but as our eyes were forced to interpret them, simple points of light. This was the elegant lie told by the vastness of space, a lie that would take millennia of relentless curiosity to unravel. To gaze upon a star was to be humbled by distance. To ask its size was to border on insanity. How do you measure a fire that rages quadrillions of miles away? How do you hold a cosmic yardstick to something so remote its light has travelled for centuries just to reach your eye? The question itself seemed to mock the very limits of human endeavour. Yet, it is in our nature to ask impossible questions. We are the descendants of navigators and dreamers who charted worlds by these same distant lights. And the impulse to know, to measure, to comprehend is woven into our very being. The quest to size the stars is not just a story of astronomical technique, it is the story of us, refusing to accept the cosmos as a mere backdrop and instead demanding to know the scale of its players. It is a detective story written in photons and gravity, played out across generations, where each discovery was a hard-won key, unlocking another door in a seemingly infinite hallway. The first step was to shatter the illusion of the celestial sphere, to prove that the stars were not equidistant. This required a tool born not of lenses, but of perspective. The ancient Greeks understood the principle, a simple trick of perception you can perform right now. Hold your thumb out at arm's length and close one eye. Note its position against a distant wall. Now switch eyes. Your thumb appears to jump. This is parallax, the apparent shift of a nearby object against a distant background. Astronomers realized that Earth itself provided the two necessary eyes. By observing a star in June, and then again in December, our planet would have travelled 300 million kilometres to the opposite side of its orbit. Surely this enormous baseline would cause a nearby star to shift its position against the backdrop of its more distant brethren. For centuries they tried. Tycho Brahe, with his magnificent island observatory, strained to see the shift, but his instruments weren't precise enough. The null result was interpreted not as a failure of equipment, but as proof that the stars were unthinkably far away, their parallax shift too minuscule to register. The silence from the stars was deafening, a testament to an unimaginable scale. It wasn't until 1838 that the silence was broken. The German astronomer Friedrich Bessel, after a grueling 18 months of meticulous observation of the star 61 Cygni, finally measured what no human had seen before, a tiny, almost imperceptible wobble. The shift was less than 1/3 of an arc-second. To appreciate this scale, imagine a coin placed more than 5 kilometers away. The angle it occupies in your vision is 1 arc-second. Bessel had measured a deviation smaller than that. It was a microscopic measurement that yielded a colossal result. For the first time, we had a concrete distance to a star other than our own. 61. Cygni was over 60 trillion miles away. The dam had broken. By turning our entire planet into a cosmic surveying instrument, we had found the first rung on the ladder to the stars. Parallax gave us a direct geometric measurement of distance, a fundamental truth upon which everything else would be built. But it was a fragile, difficult tool. It only worked for our closest cosmic neighbours. For the vast majority of stars, even Earth's orbit was too small a baseline. They were simply too far away to produce any discernible shift. A new key was needed. That key was found not in a star's position, but in its very essence, its light. We all have an intuitive understanding of how light and distance are related. A candle held a few feet away is bright. Move it 100 feet away, and its glow becomes faint. If you knew, somehow, that every candle in the world possessed the exact same intrinsic brightness, you could determine its distance based solely on how dim it appeared. This simple concept, known as the inverse square law, became the next great hope for cosmic cartography. Astronomers began a hunt for these standard candles, celestial objects whose true brightness or luminosity was known. They found them in pulsating stars called Cepheid variables, cosmic lighthouses whose pulse rate was directly tied to their intrinsic power. Find a Cepheid, measure its pulse, and you know how bright it truly is. Compare that to how bright it appears, and you can calculate its distance. This technique allowed us to leapfrog over the limitations of parallax, pushing our measurements deeper into the Milky Way and even to neighbouring galaxies. But this only gave us distance. The grand prize, the actual physical size of a star, remained elusive. We knew how far away they were, but not how big. To find that, we had to do something extraordinary. We had to learn how to read light itself. If you pass sunlight through a prism, it splits into a familiar rainbow, a continuous spectrum of colour. But in the early 19th century, a physicist named Joseph von Fraunhofer, using more precise equipment, noticed something startling. The sun's rainbow was not perfect. It was crosshatched by hundreds of fine, dark lines, mysterious gaps where specific colours were missing. For decades, these lines were a baffling enigma. It was only later that we understood we were seeing a cosmic fingerprint. As light blazes out from a star's core, it passes through the star's cooler outer atmosphere. The chemical elements in that atmosphere, hydrogen, helium, iron, each absorb light at their own unique characteristic frequencies. Those missing colours, the dark Fraunhofer lines, are the shadows cast by atoms. Suddenly, we had a Rosetta Stone for the stars. The spectrum of a star's light became its biography, a detailed report revealing its chemical composition, its temperature, its pressure, even the speed at which it was rotating. It was a revolution. We no longer just saw a point of light. We saw a place, a churning sphere of specific elements burning at a specific heat. This newfound ability to determine a star's temperature was the final, crucial piece of the puzzle. Physics dictates a fundamental relationship between the temperature of an object, its surface area, and the total amount of energy it radiates. It's known as the Stefan-Boltzmann law. A small or hot object can radiate the same total energy as a large cool object. We could now use our standard candles to determine a star's true luminosity, its total energy output, and with spectroscopy, we could determine its surface temperature. With those two values in hand, calculating the third was a matter of simple arithmetic. The star's surface area, and from that its radius, was finally revealed. We had done it. We had devised a method to hold a ruler to a bonfire 1,000 light years away. The era of stellar giants had begun. The hunt was on for the largest suns in the cosmos. For much of the 20th century, the champions were familiar names, beacons in our night sky. There was Antares, the fiery heart of the Scorpion, a red supergiant so large that if it replaced our sun, its surface would extend past the orbit of Mars. Its ruddy glow is the light of a star entering its final, dramatic phase of life, swelling to incredible proportions before its inevitable demise. Then there was Betelgeuse, the brooding shoulder of Orion, a star so famously immense it became a benchmark for cosmic scale. A similar red supergiant, its size is not static. Betelgeuse is a dynamic, pulsating behemoth, its surface boiling and churning, its very diameter in a constant state of flux. In late 2019, it dimmed so dramatically that astronomers wondered if it was on the verge of exploding into a supernova, a celestial death rattle that would be visible in daylight from Earth. These were the titans we knew, colossal spheres of plasma that dwarfed our own sun, making it seem like a grain of sand next to a beach ball. They stretched our understanding of what a star could be, pushing the known limits of stellar physics. But even these giants were destined to be dethroned. The universe, it turned out, had an even grander imagination. In the mid-2000s, a team of astronomers was poring over data from a survey of the southern sky, sifting through the light of millions of stars. Deep in the constellation of Scutum, the Shield, they found something extraordinary. It wasn't a particularly bright star, in fact, it was too dim to be seen with the naked eye. But the data told a story that was difficult to believe. The star, catalogued as UY Scuti, was a variable star, its brightness fluctuating over a period of more than 2 years. This variability, combined with its infrared signature, suggested it was a late-stage hypergiant, a rare and extreme class of star. Using the techniques perfected over the previous century, astronomers began to piece together its profile. They measured its distance, a staggering 9,500 light-years away. They analysed its spectrum, finding the telltale signs of a relatively cool surface temperature for a star, just over 3,000 degrees Celsius. But when they calculated its luminosity, the number was astronomical. It was shining with the light of over 300,000 suns, a cool temperature, but an immense luminosity. The Stefan Boltzmann law left only one possible conclusion. Ui Scuti had to be mind-bogglingly enormous. The calculations placed its radius at somewhere around 1,700 times that of our Sun. A number so large it feels abstract, meaningless. We have to bring it home to truly comprehend the monster we had discovered. So let us embark on a journey. Let us replace our familiar, life-giving Sun with this newfound king. The first thing you would notice is that the concept of day and night would cease to exist. From Earth, the star's surface would fill more than half the sky. Mercury, Venus, Earth, Mars, all would be instantly vaporized, consumed within the star's fiery atmosphere. But that is only the beginning. The actual surface of Ui Scuti, its photosphere, would stretch out far beyond the asteroid belt. It would swallow the gas giant Jupiter, the largest planet in our solar system, without a whisper. Its gravitational influence would be so immense, so commanding, that the distant orbit of Saturn would now feel like a close embrace. To fly a commercial airliner across its diameter would take over 1,000 years. Even light itself, the undisputed speed champion of the universe, would need nearly 8 hours to travel from one side of Ui Scuti to the other. It takes light just 8 minutes to reach Earth from our Sun. This star is not merely a celestial object, it is a self-contained solar system. Its volume is so vast that you could fit nearly 5 billion of our suns inside it. For years, this was the undisputed monarch of the cosmos. Ui Scuti became the new benchmark, the ultimate example of stellar gigantism. Scientists studied its shrouded, dusty shell, trying to understand the violent mass loss that fuels its instability. It was a star living on the absolute edge of possibility, a physical manifestation of the upper limits of mass and energy a star can contain before it tears itself apart. The textbooks were rewritten. The old champions, Betelgeuse and Antares, were relegated to the roles of provincial lords in the court of an emperor. Ui Scuti was the final answer, the triumphant culmination of a 200-year quest to measure the immeasurable. It seemed the story of cosmic titans had found its final chapter. The mountain had been climbed, its breathtaking peaks surveyed and mapped. But science is a story that never truly ends. Its chapters are written in pencil, not ink. And even as Ui Scuti reigned supreme, a ghost was waiting in the archives of a different sky survey, an unassuming data point logged decades earlier. It was an anomaly hidden in plain sight within a dense, overlooked cluster of stars. An object so extreme, so impossibly large according to the initial readings, that it was dismissed as an error, a flaw in the data, a miscalculation. Because to accept it as real would mean that our understanding was incomplete. It would mean that the yardstick we had so carefully crafted was somehow flawed, or that the universe had produced a monster that defied our most fundamental theories. A shadow was stirring, a presence that suggested the mountain we had just climbed, the one that took all our ingenuity to scale, was merely a foothill on the path to something truly incomprehensible. For a time, we thought we had found the edge of possibility. In the crimson glow of Ui Scuti, humanity had discovered a monster, a star so grotesquely swollen it seemed to defy the very physics that had given it birth, a celestial sovereign at the known limits of size. It became our benchmark for the Colossal, the ultimate yardstick against which all other stellar giants were measured and found wanting. We had crowned our king, and the cosmos, it seemed, had shown us its hand. But the universe is a profoundly humble place for those who claim certainty. Its grandest secrets are seldom paraded in the open. They are whispered from behind impenetrable veils, hidden not in the empty voids between galaxies, but right here, in our own home, tucked away in the most crowded, chaotic and visually hostile neighbourhoods of the Milky Way. The search for the true monarch of the stars required us to look not at the brightest points of light, but into the deepest darkness, into a region of our galaxy so choked with dust and gas that it appears to the naked eye as a river of absolute nothing. This celestial dead zone lies in the direction of the constellation Scutum, the Shield, a fitting name for a region that guards its secrets so fiercely. Here, some 18,900 light-years from Earth, the majestic spiral arm of our galaxy begins to curve inward, a grand, sweeping causeway of stars on its journey toward the galactic core. This is not the serene, sparsely populated neighbourhood our sun enjoys. This is the city centre at rush hour, a violent, seething metropolis of stellar creation and destruction, a place where the universe is still hot from the forge. Thick, roiling clouds of hydrogen, carbon, and silicate dust, the accumulated soot of billions of years of stellar life and death, hang like an impenetrable smog, blotting out the light from behind. To optical telescopes, this is a cosmic cataract, a blind spot on the grand map of our galaxy, a frustrating wall of blackness. It was precisely into this wall that we had to stare, because hiding within it was a prize beyond imagining. Our journey begins not with a gleaming modern space telescope, but with the patient, methodical work of an American astronomer in 1990. Charles Stephenson, using photographic plates sensitive to deep red light, was meticulously cataloguing new types of stars, particularly carbon stars, in the northern summer sky, a process akin to taking a census of a city shrouded in a perpetual thick fog. He was not hunting for monsters, he was simply trying to see what was there. In his survey, he identified a faint anonymous grouping of stars, a tiny, almost insignificant smudge on his plates, which he labelled simply Stephenson 2. At the time, it was just another entry in a catalogue, a footnote in a paper. No one could have known that this unassuming little cluster was not a quaint village of ordinary stars, but a den of titans. It was a gravitational island, a rare open cluster, but one populated almost exclusively by red supergiants, the dying, bloated embers of the most massive stars the galaxy can produce. Imagine finding an island inhabited solely by blue whales, and you begin to grasp the sheer improbability, the sheer statistical anomaly of Stephenson 2. This was a place where the normal rules of stellar evolution seemed to be pushed to their absolute breaking point, a cosmic retirement home for the most gargantuan stars in the Milky Way, all gathered together in one place. And within this gathering of giants, one of them, the 18th star catalogued in the cluster, was destined to rewrite our understanding of what a star could be. But to see it, to even begin to comprehend it, we had to abandon our eyes. Visible light, the beautiful spectrum of colours that paints our world, is utterly useless here. The particles of interstellar dust are perfectly sized to scatter and absorb these wavelengths, effectively making the region opaque. Trying to view Stephenson 218 in visible light is like trying to see the filament of a light bulb through a mile of dense black smoke. It is an exercise in futility. The secret, the key to unlocking this part of the universe was heat. It was a different kind of a light, a form of radiation our eyes cannot perceive, but which carries the fundamental signature of existence: infrared. Infrared astronomy became our superpower, our technological cheat code. While visible light is stopped cold by the cosmic dust, longer infrared wavelengths, which we perceive as thermal energy, can slip through the gaps between the dust grains with far greater ease. It's the difference between trying to throw a fistful of sand through a screen door and throwing a handful of marbles. The marbles get through. Suddenly, with telescopes designed to see in these infrared bands like the 2-micron all-sky survey or 2MASS, the darkness began to part. The great dusty veil of the Scutum-Centaurus arm was rendered translucent, and for the first time we could peer into the ghost-haunted heart of the cluster. What we saw was breathtaking. The faint smudge from Stephenson's plates resolved into a tight knot of searingly bright points of light, each one a star of unimaginable scale. They were like distant bonfires glimpsed through a thick forest fog, their true nature still obscured, but their immense power undeniable. And there, among its colossal brethren, was the star-designated Stephenson 218. Even in this initial blurry heat vision view of the cosmos, it was immediately shockingly different. It wasn't just bright, it was overwhelmingly prodigiously luminous. It radiated energy on a scale that felt almost like a numerical error, a furious beacon burning with the light of nearly 500,000 suns. This raw power, this sheer wattage, was the first clue that we were looking at something that broke the mold, something that might even challenge UI Scuti. A star's luminosity is directly tied to its size. To shine that brightly, a star must have an enormous surface area from which to radiate. The initial calculations, even the most conservative ones, were staggering. But this immense brightness presented a profound and deeply confusing paradox. To get a true measure of a star, we need more than just its brightness. We need to understand its temperature, its chemical makeup, its very soul. And for that, we turn to one of the most powerful tools in astrophysics, spectroscopy. By capturing a star's light and splitting it through a prism, we can see its spectrum, a celestial barcode that reveals the chemical elements burning in its atmosphere. Each element absorbs light at specific unique frequencies, leaving dark lines in the rainbow of starlight, a perfect chemical fingerprint. When astronomers finally managed to capture the faint dust-filtered infrared light from Stephenson 218 and decode its spectral fingerprint, the results only deepened the mystery. The barcode was unambiguous. It was littered with the telltale absorption lines of exotic molecules like titanium oxide and vanadium oxide, signatures that can only form in the relatively placid, cool outer layers of a star's atmosphere. This was the definitive spectral class of an M-type star, a red supergiant. Its surface temperature was incredibly low, barely 3,200 degrees Kelvin. That's cooler than the filament in an old incandescent light bulb. It was, for all intents and purposes, a celestial ember. Herein lies the contradiction that baffled everyone. How can an object be one of the most luminous things in the entire galaxy, blazing with the power of 440,000 suns, while simultaneously having one of the coolest surface temperatures for any supergiant? It's like discovering a campfire that is somehow outshining a lighthouse. The two facts seem mutually exclusive. They fight each other. There is only one mind-bending way to reconcile them. If each square meter of the star's surface is relatively dim and cool, then to produce such an insane total amount of light, the star must possess a truly biblical number of square meters. Its surface area, its sheer physical size, had to be beyond all known precedent. The cool temperature and the extreme luminosity were not a contradiction at all. They were two independent lines of evidence pointing to the same terrifying conclusion. This star was bigger than anything we had ever dared to imagine. The initial tentative estimates based on this spectral data began to trickle in, and they were far more audacious than those from the brightness measurements alone. They suggested a star not just larger than UI Scuti, but in a completely different league. Yet this tantalizing glimpse was fraught with colossal uncertainty. The very dust that had hidden the star for so long was now actively working to deceive us, to corrupt the very data we were using to measure it. The problem is a phenomenon known as interstellar extinction and reddening. As the star's light struggles through those 19,000 light-years of cosmic grit, it doesn't just get dimmed. Its colour profile is fundamentally altered. The dust is more effective at scattering shorter, bluer wavelengths of light, allowing the longer, redder wavelengths to pass through more easily. It's the same principle that makes a sunset appear red. As the sunlight passes through more of Earth's atmosphere, scattering the blue light away. Now, amplify that effect over a distance of 100 quadrillion miles. The light that finally reaches our telescopes from Stephenson 2-18 is profoundly, artificially reddened. Like looking at the world through a pair of deep crimson sunglasses we can never take off. This distortion is an astronomer's nightmare. It poisons the data, making it incredibly difficult to know the star's true intrinsic brightness or its precise original temperature. Are we seeing a truly cool star, or just a hotter star that has been heavily reddened by the intervening dust? Is its luminosity truly that high, or are we underestimating how much of its light is being blocked, a factor we call its extinction value? Every calculation was plagued by error bars the size of solar systems. Pinning down the exact properties of Stephenson 2-18 became less like a measurement and more like an act of cosmic forensics, an attempt to reconstruct a crime scene from a single smudged fingerprint found on a foggy window. The scientific community was split. Some saw the data as a revolutionary signpost, pointing toward a new class of stellar leviathan. Others remained deeply skeptical, arguing that the uncertainties were simply too great, that the extreme values were likely artifacts of our flawed models of how light interacts with the interstellar medium. UY Scuti, its properties far more reliably measured due to its clearer line of sight, remained the reigning verifiable champion. The Stephenson 2 cluster was a tantalizing enigma. It was a collection of the galaxy's most extreme objects, all clustered together, offering a unique laboratory for studying the final spectacular stages of massive stars. Yet this laboratory was locked behind a near-impenetrable wall of dust. The spectroscopic hints were there, whispering of a new king. The impossible combination of cool temperature and brilliant luminosity formed a compelling, almost irresistible piece of circumstantial evidence. We had found a suspect, a colossal shadow lurking in the Milky Way's darkest alley. But suspicion is not proof. To dethrone UY Scuti, to definitively crown this new monarch of the cosmos, we would need more than just a spectral ghost. We would need a new way of seeing, a new technique so precise it could cut through the interstellar fog and measure the star directly. We had to find a way to place a celestial ruler across 19,000 light-years of hostile space, to bypass the deceptions of dust and distance, and to ask the star a simple question: just how big are you really? The challenge seemed insurmountable, but the potential reward, the chance to gaze upon the face of the largest star in our universe, drove a new generation of astronomers to devise some of the most ingenious observational methods ever conceived. The case for Stephenson 2-18 was about to be made, not with estimations and models, but with the cold, hard light of empirical evidence. And so, the gauntlet was thrown. Across 19,000 light-years of interstellar void, a challenge had been issued not in words, but in photons. Stephenson 2-18, this faint ruddy ember nestled within its crowded stellar nursery, was more than just a distant point of light. It was a cosmic enigma, a puzzle box locked by distance and veiled in nebular dust. The initial hints were tantalizing, the whispers from early surveys suggesting a scale that bordered on the impossible. But hints are not facts, and whispers are not proof. To truly know this star, to measure its magnificent dimensions and potentially rewrite the celestial record books, science would need more than a simple telescope. It would require a forensic investigation on a galactic scale, an autopsy of light that had been travelling since before human civilization began. The question hanging in the air, a silent weight in every observatory control room, was immense. Were we looking at a genuine titan, a star that defied our understanding of stellar physics? Or were we simply being deceived by a trick of light, an artifact of the cosmic dust that littered the path between our world and this distant giant? The observational battle to crown a new king of the stars had begun, and the first front in this war for truth would be fought in a realm of light invisible to our own eyes. To pierce the dusty shroud enshrouding the Stephenson 2 cluster, astronomers turned to their most powerful secret weapon, infrared light. Think of it as a form of cosmic vision that sees not the brilliant glare of a star, but its fundamental heat, its deep, resonant thermal glow. While visible light, the kind our eyes detect, is easily scattered and absorbed by the fine grains of interstellar dust, like headlights in a thick fog. Longer infrared wavelengths pass through almost unhindered. They carry a more pristine message from the star itself. We had to abandon the light that shows us a star's sparkle and instead seek the radiation that tells us of its soul. Using orbital sentinels like the Spitzer Space Telescope and the Wide-Field Infrared Survey Explorer, humanity's infrared eyes in the sky, astronomers began a painstaking process of collection. For months, these incredible instruments stared into the heart of the Scutum-Centaurus arm, gathering photons one by one, building an image not of how Stephenson 2-18 looks, but of how it feels. This is the art of infrared photometry, the meticulous measurement of brightness at specific invisible wavelengths. Each photon captured was a clue, a tiny packet of energy that had completed its 19 millennia journey. The data streamed back to Earth, not as a beautiful photograph, but as endless columns of numbers, a digital ghost of the star's thermal signature. Scientists had to sift through this deluge of information, carefully subtracting the light from neighbouring stars and accounting for the faint thermal glow of the background dust itself. It was like trying to hear a single, pure note in the middle of a roaring orchestra. They were isolating the unique energy fingerprint of Stephenson 2-18. What they began to assemble was the profile of an object radiating energy on a stupendous scale. The sheer quantity of infrared light pouring from it was staggering. This was no ordinary red supergiant. The numbers suggested a luminosity hundreds of thousands of times greater than our own sun. A furnace so vast it was pouring out energy, equivalent to nearly 500,000 suns combined. This was the first piece of solid evidence, the first truly undeniable clue that something extraordinary was taking place deep within the Milky Way. But luminosity, for all its grandeur, does not equal size. A smaller, incredibly hot star can be just as luminous as a larger, cooler one. To get the radius, to find the true physical size, we needed another critical piece of the puzzle, the star's temperature. By analysing the spectrum of the infrared light, the precise balance of different wavelengths, astronomers could take the star's temperature from across the galaxy. The light from a cooler star peaks at longer, redder wavelengths, while a hotter star's light shifts towards the blue. Stephenson 2-18's light was overwhelmingly, profoundly red. Its spectral signature screamed that it was a celestial iceberg, not a fireball. The models indicated a surface temperature of only about 3200 Kelvin. To us, this sounds incredibly hot, a temperature that would vaporize any known material. But for a star, this is exceptionally cool, bordering on frigid. It placed Stephenson 2-18 firmly in the category of the coolest, most evolved red supergiants. And here, the breathtaking logic of physics took hold. If you have an object that is only moderately hot, yet it is putting out an absolutely colossal amount of energy, there is only one possible explanation. That object must be incomprehensibly, unbelievably vast. The sheer surface area required to radiate that much energy at such a low temperature had to be larger than anything we'd ever confidently measured. The initial calculations were so extreme that they were met with skepticism, even by the teams who performed them. The numbers pointed to a radius of over 2,000 times that of our Sun. A star so large that if it replaced our Sun, its surface would extend beyond the orbit of Saturn. It was a result that felt like a fantasy, a conclusion so profound it demanded more proof. The infrared data had opened the door, but to walk through it, we needed to corroborate this finding with a completely different method, a technique that would let us feel the very breath of this distant monster. For this next step, we had to stop looking at the star itself and start listening to its immediate surroundings. We turned from light to sound, or at least the cosmic equivalent. Red supergiants like Stephenson's 2-18 are not serene, stable spheres. They are dying stars, great throbbing hearts that are actively shedding their outer layers into space. In their final, dramatic chapters, they blow off enormous stellar winds, creating vast, expanding shells of gas and dust that envelop them like a cocoon. And within these shells, a strange and wonderful phenomenon occurs. Certain molecules, like silicon monoxide, when energized by the star's faint light, can become agitated in a very specific way. They absorb energy and then release it in a concentrated, coherent beam of microwave radiation. This is a maser, the microwave equivalent of a laser. These masers, embedded in the star's outflowing atmosphere, act as natural amplifiers, cosmic beacons broadcasting a precise radio frequency. And for astronomers, they are a gift from the universe. Using arrays of powerful radio telescopes, like the Very Large Array in New Mexico, we can tune in to these maser emissions. We can listen to the whisper of silicon monoxide molecules 95 quadrillion kilometers away. This is not just an act of cosmic eavesdropping, it provides a crucial diagnostic tool. Because these masses are moving away from the star along with the rest of the outflowing gas, their signal is subject to the Doppler effect. The signal from the gas moving towards us is shifted to a slightly higher frequency, or blue shifted. The signal from the gas on the far side of the star moving away from us is shifted to a lower frequency, or redshifted. By measuring the precise extent of this shift, we can calculate the velocity of the expanding shell of gas with incredible accuracy. We are, in effect, measuring the speed of the star's own breath. For Stephenson 2-18, the maser signals painted a clear picture of a star shedding its mass at a steady, inexorable pace. But more importantly, the physical distance between the blue-shifted masers on the front side and the red-shifted masers on the back side gives us an independent geometric measurement. It provides a physical ruler, a way to gauge the scale of the star's immediate environment. This data, when combined with the star's known distance, gave astronomers another anchor point, another piece of evidence that constrained the possible size of the central engine powering this entire system. The maser emissions acted as a crucial cross-check. They confirmed that we were indeed observing a colossal evolved star in the late stages of its life, one that was actively puffing its atmosphere out into the cosmos. The infrared photometry had given us a ghost, a thermal spectre of immense proportions. The maser analysis gave that ghost a heartbeat, a dynamic quality that spoke of its physical reality. Now, with two powerful but separate lines of evidence pointing towards an unprecedented size, it was time to unite them, to forge them into an unassailable conclusion. This required the most powerful tool of all, the human mind, amplified by the world's most powerful supercomputers. The final phase of the investigation was a journey into the virtual. It was no longer enough to just observe. Scientists had to build Stephenson 2-18 from the ground up, inside a machine. This is the realm of radiative transfer modelling, a discipline that is part astrophysics, part computer science, and part artistry. The goal is to create a digital twin of the star, a perfect computer simulation that behaves exactly like the real thing. It begins with a set of assumptions. The computer is given a virtual sphere of plasma with a certain mass, a certain chemical composition, a certain temperature, and a certain radius. Then the simulation begins. The laws of physics are unleashed. The model calculates how energy, born from nuclear fusion deep in the star's core, would fight its way to the surface. It simulates how that energy would be absorbed and re-emitted by countless atoms in the star's bloated atmosphere. It calculates how that light's journey would be affected by the expanding shells of gas and dust surrounding the star, the very shells whose velocities were measured by the master emissions. Finally, the simulation produces its own version of what a telescope on Earth would see. It generates a synthetic spectrum, a prediction of the star's brightness across all the infrared wavelengths. And then comes the moment of truth. The scientists take this synthetic data, this output from their digital creation, and they lay it directly on top of the real data collected by the Spitzer telescope. At first, the match is always poor. The virtual star might be too bright in one wavelength, too dim in another. The shape of its spectral curve might be completely wrong. And so, the painstaking work of refinement begins. The astronomers go back to the model and tweak the cosmic dials. What if the star is slightly cooler? They adjust the temperature parameter and run the entire simulation again, a process that can take hours or even days of supercomputer time. The new result is compared. Better, but still not right. What if the surrounding dust shell is thicker? They change the dust density parameter, run it again. What if the stellar wind is faster, matching the maser data more closely? Tweak, simulate, compare, repeat. This is a relentless, iterative process, a form of celestial sculpting. For Stephenson 2-18, this was a monumental task. The team ran hundreds, then thousands of simulations, exploring every plausible combination of parameters. They were methodically eliminating every possibility that did not perfectly match the observed reality. They were forcing the ghost in the machine to become identical to the giant in the sky. Slowly, painstakingly, with each new run, the simulated data began to converge with the real-world observations. The jagged lines of the model's output spectrum started to align, to perfectly overlay the smooth curve of the data beamed back from space. The digital twin was coming to life. The model, now constrained by the infrared photometry, the massive velocities, and the star's estimated distance, was finally settling on a stable, self-consistent solution. a solution where all the disparate pieces of evidence clicked into place, supporting and reinforcing one another. There was a moment in front of a computer screen where the final simulation finished running, a moment where the red line of the model perfectly traced the black line of reality. In that silent digital space, the truth was finally laid bare, stripped of all ambiguity and observational distortion. The model had found the one unique combination of temperature, luminosity, and radius that could explain everything we had seen. And the number it produced for the radius was not just big, it was revolutionary. The computer confirmed the initial estimates with terrifying precision. The final verified radius for Stephenson 2-18 was calculated to be 2,050 times that of our Sun, a diameter of nearly 3 billion kilometers. It was a figure that demanded silence, a moment of profound, humbling awe. In that moment, a monarch fell. For years, the undisputed king of the stars had been Scuti, another colossal red supergiant. Its estimated radius, at around 1,700 times that of the Sun, was already a number that strained the imagination. It had long served as the ultimate benchmark for stellar gigantism, the undisputed heavyweight champion of the cosmos. Astronomers spoke of it with reverence, the outer limit of what was thought possible for a star to be. But the new, rigorously tested data for Stephenson 2-18 did not just challenge Scuti's record, it obliterated it. A radius of 2,050 solar radii is not a small increase. It represents a star with a volume nearly 3 times greater than that of Scuti. Imagine the Sun as a single grain of sand. On this scale, Scuti would be a sphere 1.7 meters across. But Stephenson 2-18 would be a sphere towering over 2.1 meters in diameter, a gargantuan object that fundamentally redefines the meaning of the word large. A beam of light, the fastest thing in the universe, would take over 9 hours to complete a single journey around its circumference. Over 10 billion suns could fit inside it. The verdict was clear, the evidence undeniable. The reign of Scuti was over, the crown had been passed. Science had officially, definitively, crowned a new, even more magnificent king. But this discovery was more than just a new entry in a cosmic record book. It was a shockwave sent through the very foundations of stellar theory. Finding a star this enormous forces us to confront unsettling questions about our own understanding. The established models of stellar evolution, the complex computer codes that predict how stars live and die, had always suggested an upper limit to how large a star could physically become. This theoretical barrier, known as the Hayashi limit, defines a boundary beyond which a star should not be able to maintain hydrostatic equilibrium. A star that grows too large should, in theory, become catastrophically unstable and collapse or tear itself apart. Stephenson 2-18 does not just approach this limit, It pushes right up against it, perhaps even teetering on its very edge. It exists in a state that our physics struggles to fully explain. How can a single, gravitationally bound object maintain its structure on such an impossibly bloated scale? What forces are at play in its interior that prevent it from simply dissipating into space? The dethroning of Scuti was the end of one story, but the coronation of Stephenson 2-18 was the beginning of a much deeper, more profound mystery. We had set out to measure a star, and in doing so, we had found a paradox, an object that seems to defy the known laws of its own existence. It is a beautiful, terrifying monster that now compels us to look again at our theories, to sharpen our pencils, and to ask a very simple, yet universe-altering question. How is this possible? And so, we stand in the shadow of a colossus. The measurements are in, the calculations confirmed, and the sheer, breathtaking scale of Stephenson 2-18 has been laid bare. It is not merely a record holder, it is a monster that lives in the twilight realm between scientific theory and outright impossibility. To gaze upon its image, a tiny crimson smudge swimming in a sea of lesser lights, is to confront a profound cosmic paradox. For having now grasped its size, we are forced to grapple with a far more unsettling question. How can such a thing even exist? The laws of physics, as we understand them, are not just rules, they're guardrails against excess. They dictate the limits of what is possible, imposing a ceiling on mass, on luminosity, on size itself. Yet here is a star that seems to mock those limits, a creation so extreme it pushes our most trusted models of stellar evolution to the very brink of collapse. Its existence is a challenge thrown down to the heart of astrophysics, demanding that we reconsider the story of how stars live and, ultimately, how they die. This is not just a bigger star. This is a different order of being. To understand the crisis Stephenson 218 represents, you must first understand the violent engine that powers it. Deep within its core, pressures and temperatures reach levels that defy earthly comparison. It is a thermonuclear heart, a raging inferno where atoms are not merely fused but annihilated in a continuous frantic blaze. Unlike our Sun, which calmly fuses hydrogen into helium in a process that will sustain it for billions of years, a hypergiant like this one burns through its fuel with a reckless, desperate abandon. It is a celestial furnace with its throttle jammed wide open. The sheer volume of its core means fusion isn't just happening at its centre. It is raging through concentric shells, each layer burning a heavier element than the one above it. Hydrogen, helium, carbon, neon, oxygen, silicon. A frantic cascade of creation, forging the heavy elements that will one day seed new worlds, but at a terrible immediate cost to the star itself. This furious engine generates a torrent of energy so immense it beggars belief. Its luminosity is not measured in thousands, but in hundreds of thousands of times that of our own Sun. It radiates more light in a single minute than our star does in an entire year. This isn't just a glow, it is a physical force, an unrelenting, outbound hurricane of photons, a pressure wave of pure light that slams against the star's own material from the inside out. This outward force, known as radiation pressure, is the star's eternal enemy in the war against its own gravity. Gravity, the star's immense mass, relentlessly tries to crush it all inward into an infinitesimal point. Radiation, the product of its fusion, desperately pushes outward to keep it inflated. In a stable star like our Sun, these two forces exist in a delicate, lifelong equilibrium. But Stephenson 218 knows no such peace. Its equilibrium is a lie. It lives its life on a gravitational knife edge, a constant violent struggle where the outward push of light is so powerful it nearly overcomes the inward pull of gravity. It is perilously close to what is known as the Eddington limit, a theoretical boundary beyond which a star's luminosity would be so high, its radiation pressure so intense that it would literally blow itself apart. It would tear its own outer layers to shreds, unable to contain the fury of its own core. This star lives its entire frantic life hovering just beneath that catastrophic threshold. It is a gravitational dam holding back a universe of light, with cracks already beginning to show. The structure is failing, not in a sudden cataclysm, but in a slow, majestic and inexorable process of self-dismantling. The evidence of this failing structure is written across thousands of light-years of space. It is the star's stellar wind. For a star this luminous, the term wind is a hopelessly gentle misnomer. This is no celestial breeze. It is a cosmic hemorrhage. The same radiation pressure that holds the star up is also powerful enough to grab hold of its tenuous, bloated outer atmosphere and blast it violently into the void. It is a celestial blowtorch, actively sandblasting its own surface away, molecule by molecule, layer by layer. Every second it ejects tons of its own substance into the interstellar medium. Over the course of a single year, it sheds a mass equivalent to several times that of our entire planet. While our Sun loses a tiny fraction of its being over its entire 10 billion year lifespan, Stephenson 218 is visibly unravelling before our eyes. Astronomers see the ghost of this process surrounding the star. A vast, intricate and turbulent nebula of expelled gas and dust envelops it, a ghostly shroud woven from the star's own cast-off skin. This isn't just a static cloud, it is a dynamic, evolving record of the star's violent history, showing shells of material ejected during particularly unstable epochs. Studying the chemistry of this surrounding veil, we find it is rich in the heavier elements forged in the star's core and dredged up to the surface by violent convection currents. We are in effect seeing the star's insides turned out. It is bleeding its lifeblood into the cosmos, enriching the Stephenson 2 cluster with the raw materials for future generations of stars and planets. But in doing so, it is diminishing itself. The behemoth we measure today is, paradoxically, a shadow of its former self. To have reached this stage, it must have started its life with an even more unthinkable mass, perhaps 50, 60, or even more times the mass of our Sun. It has already shed entire solar systems worth of material to become the giant we see now. This immense mass loss is not merely a consequence of its size. It is a fundamental driver of its evolution. It is the mechanism by which the star desperately tries to regain stability, shedding the excess weight that fuels its near-catastrophic luminosity. Yet this process itself creates a feedback loop of instability. As the outer layers are stripped away, we see deeper, hotter, more volatile layers of the star. The star's very appearance changes, its temperature and colour shifting over timescales that are, astronomically speaking, the blink of an eye. In the past, it may have been a hotter, bluer star. Today, it is a bloated, cool red hypergiant, its vast surface area allowing it to radiate away its immense energy at a lower temperature. Its colour is the colour of a dying ember, an ember the size of our solar system. Its ruddy glow is not a sign of health, but a symptom of its advanced terminal age. And this is where our models begin to fray and tear. The established theories of stellar evolution, painstakingly built over a century of observation and calculation, struggle to account for a creature like this. The first, most fundamental problem is one of birth. How does a star accumulate so much mass in the first place? When a protostar is forming from a collapsing cloud of gas and dust, it begins to heat up. As it grows, its burgeoning radiation pressure starts to push back against the very material that is falling into it. For most stars, there is a natural limit, a point where the outward push becomes so strong that it halts any further accretion. It effectively cuts off its own food supply. For a star to grow to the initial mass required to become Stephenson 218, it would have had to somehow bypass this fundamental restriction. Did it form in an environment of unimaginable density, where material was forced onto it faster than it could push it away? Or, as a more tantalizing theory suggests, was it not born, but made? Perhaps what we are seeing is not a single star, but the product of a series of cataclysmic mergers. In the chaotic, crowded heart of the young Stephenson 2 cluster, multiple massive stars born in close proximity may have spiraled into one another in a gravitational dance of death, their cores and envelopes combining to create a single, monstrous entity. This process, a form of stellar cannibalism, would provide a pathway to accumulating a mass that is forbidden by conventional formation models. The star would be a Frankenstein's monster, stitched together from the remnants of its siblings, its turbulent, oversized structure, a direct consequence of its violent origins. The dynamics of such a merger are terrifying to contemplate, an event that would have reshaped the entire stellar cluster. Even if we can solve the puzzle of its birth, we are left with the crisis of its life. How does it remain even remotely stable? The internal physics are a nightmare of complexity. The star is so large that its outer layers, extending out to where the orbit of Saturn would be in our solar system, are bound to the core by a surprisingly tenuous thread of gravity. They are practically floating, a shimmering convective soup thousands of times less dense than the air you are breathing now. Convection cells, rising bubbles of hot plasma the size of entire countries or even small planets, would churn its surface in a slow, boiling motion. This creates immense instabilities. The star likely pulsates dramatically, swelling and shrinking over periods of months or years, its brightness fluctuating as it struggles to find a stable rhythm. Furthermore, its sheer rotational speed presents another paradox. As stars contract, they spin faster like an ice skater pulling in their arms. If Stephenson 2-18 formed from a single collapsing cloud, its rotation should be incredibly fast, potentially fast enough to flatten it into an oblate shape and fling material from its equator. Yet, Observations suggest it spins relatively slowly. The powerful stellar winds may be acting as a brake, carrying away angular momentum and slowing the star's rotation over time. Or perhaps a merger of two stars spinning in opposite directions could have cancelled out their momentum, resulting in a single, slower spinning giant. Every clue we gather seems to open a new line of inquiry, revealing layers of complexity we had never imagined. The models that work so well for 99.9% of the stars in the universe simply break down at this scale. They fail to predict its stability, its mass loss rate, and its evolutionary path with any certainty. We are in uncharted territory. Stephenson 218 is not an anomaly we can dismiss. It is a profound statement from the universe that our understanding is incomplete. It forces us to add new physics to our simulations, accounting for extreme rotation, powerful magnetic fields, and the intricate dynamics of binary mergers in dense clusters. The star is a living laboratory, a place where the most extreme physics in the cosmos are playing out in real time. It is a specimen that stretches our computational and theoretical capabilities to their absolute limit. We are like ancient cartographers faced with a report of a continent far larger than any they believed could exist on Earth. Our first instinct is to dismiss it as a fable, but when faced with the undeniable evidence, we are forced to redraw the entire map. This star is redrawing our map of the cosmos. Its immense trembling surface, its furious self-destructive winds, and its baffling stability are not just academic puzzles. They are the visible symptoms of a deep internal struggle. We are witnessing a titan wrestling with its own soul, a battle between the fundamental forces of nature playing out on a stage 1 billion times larger than our world. It is a battle that gravity in the end cannot win. The star's glorious, impossible existence is temporary. The very forces that make it so magnificent are the same forces that are actively destroying it, pushing it relentlessly toward a truly spectacular end. The deep, crimson light we see today, having travelled for 20,000 years to reach our telescopes, is the light of a dying king. The questions it poses about its life are inextricably bound to the final cataclysmic act of its death, an explosion that will be so powerful it will defy the very concept of an ending. And so we watch it, this colossal, flickering ember, adrift in the deep night of the Scutum-Centaurus arm. We have charted its impossible dimensions and felt the phantom heat of its ancient light. We have peeled back its cloudy, gossamer layers to glimpse the furious engine within. But for a star this large, for a celestial object living so close to the absolute theoretical limits of existence, life is a frantic, desperate, and ultimately fleeting affair. Its very size, the quality that inspires our deepest awe, is also its death sentence. It is burning through its vast reserves of fuel at a rate that defies comprehension. A profligate king spending an empire's fortune in a single glorious night. Every second it fuses hundreds of millions of tons of hydrogen into helium, but that is a game for younger, more stable stars. Stephenson 2-18 has long since exhausted the primary fuel of the cosmos. Deep within its convective, boiling core, a far more desperate and elemental alchemy is underway. Here, in a crucible of unimaginable temperature and pressure, the star has been climbing the periodic table. Helium has been fused into carbon, the backbone of the life. Carbon has been compressed into neon and oxygen, the breath of worlds. Oxygen has yielded silicon, the stuff of rock and sand. Each stage of this cosmic manufacturing process buys the star a little more time, a brief stay of execution against the relentless, crushing force of its own gravity. Each new, heavier element provides a burst of outward pressure, a temporary reprieve. But the clock is ticking down, and the returns are diminishing. Hydrogen fusion can sustain a star for billions of years. Helium fusion might last for 1 million. For a titan like Stephenson 2-18, the later stages of carbon, neon and silicon burning are a frantic sprint. These phases may last only centuries, then decades, then years, and finally mere days. The star is consuming its own heart to stay alive. And at the end of this desperate chain of creation lies a final, immutable dead end, a substance that marks the point of no return. Iron, The fusion of elements lighter than iron releases energy, powering the star and holding gravity at bay. But to fuse iron into anything heavier requires an input of energy. It does not produce it. Iron is the final ash of the nuclear furnace, an element that will not burn. When the core of Stephenson 2-18 finally becomes a dense, inert ball of iron, the star's long and violent life is, for all intents and purposes, over. The outward pressure from fusion, the force that has supported quintillions of tons of stellar material for millions of years, vanishes. It doesn't fade away, it simply turns off. In that instant, a silence falls at the heart of the maelstrom, and gravity, the patient, ever-present victor in all cosmic struggles, finally wins. What happens next is one of the most violent and complex events in the known universe. The star's immense outer layers, suddenly robbed of their support, begin to fall inward. A sphere of gas with a radius of nearly 10 astronomical units, a structure so vast it would swallow the orbit of Saturn, begins to collapse upon itself. The speed of this collapse is breathtaking, reaching velocities of over 70,000 kilometers per second, a quarter of the speed of light. The entire gargantuan star is thundering down towards its own center. This is the precipice, the final branching path in the story of Stephenson 2-18. From this single cataclysmic moment of core collapse, its destiny will splinter into one of several spectacular, terrifying, or eerily quiet possibilities. Each outcome will ripple through its galactic neighborhood, and each holds profound implications for our understanding of the cosmos. For most massive stars, this is the trigger for a final glorious act of defiance, a supernova. As the outer layers slam into the newly formed, impossibly dense neutron core, they don't just hit it, they rebound. A shockwave of unimaginable power is born from this cosmic bounce, this outward propagating wave of pure energy, reinforced by a stupendous blast of ghost-like particles called neutrinos, begins to tear through the infalling stellar material. It becomes a runaway thermonuclear explosion. The star, in its final moment, detonates. If Stephenson 2-18 were to go supernova, it would be a spectacle unseen in our galaxy for centuries. From our vantage point 16,000 light-years away, it would suddenly flare into view. Overnight, a new and brilliant star would appear in our sky, a celestial beacon easily visible to the naked eye. It would likely outshine every other star in the night, perhaps even rivaling the brilliance of Venus. A final, spectacular death cry made visible across a vast swathe of the Milky Way. For any potential life on planets orbiting nearby stars within the Stephenson 2 cluster, the event would be an apocalypse. A wave of high-energy radiation, X-rays and gamma rays, would wash over them, sterilizing surfaces and stripping away atmospheres. The light would be blinding, a new sun ignited in their sky, followed by a slower-moving tsunami of stellar debris that would scour their systems for millennia. But from the ashes of this destruction, creation would begin anew. The expanding shockwave, ploughing through the interstellar medium, would compress clouds of gas and dust. It would be a cosmic snowplow, creating pockets of such high density that their own gravity would take over. The death of this one colossal star would trigger the birth of a new generation of hundreds, perhaps thousands, of smaller suns and their attendant worlds. The supernova remnant, the ghostly expanding shell of the star's former self, would glow for thousands of years. A delicate, intricate shroud of superheated gas, laced with the heavy elements forged in the star's life and its explosive death. It would become a celestial memorial, a testament to the Titan that once was, and a fertile nursery for the stars that are yet to be. This is the classic time-honoured end for a stellar heavyweight, a cycle of death and rebirth played out on a galactic stage. But Stephenson 2-18 is not a classic heavyweight. It is an outlier, a monster. And for monsters, there are more monstrous ends. The sheer mass of this star opens the door to a far more violent and far more terrifying possibility. It may not just produce a supernova, it may unleash a hypernova. This is not simply a bigger, brighter explosion. It is a different kind of beast entirely, an event so energetic it can be seen across the entire observable universe. The physics behind a hypernova are rooted in the extreme conditions that only the most massive stars can create. As the core of Stephenson 2-18 collapses, its mass may be so great that not even the combined strength of neutrons can halt the implosion. Gravity overwhelms all other forces. The collapsing core doesn't form a neutron star. It continues to shrink, past the point of no return, and is crushed into a singularity. A black hole is born in the heart of the dying star. But the rest of the star is still falling inward. A swirling, superheated vortex of stellar material, an accretion disk, forms around the newborn black hole. This disk spins at incredible speeds, dragging space-time with it, whipping the black hole's powerful magnetic fields into a frenzy. And from this chaotic, churning engine, something new and terrible is unleashed. 2 opposing jets of plasma, 2 celestial blowtorches, are launched from the poles of the black hole. Confined by the infalling material of the star itself, and accelerated to more than 99% the speed of light, these jets are the most focused and destructive forces in nature. They are the universe's death rays. They blast their way outward, punching through the star's collapsing outer layers like a bullet through a mountain. When these relativistic jets finally break free into space, they announce themselves to the cosmos with an incandescent flash of the most energetic light there is, gamma rays. This is a gamma ray burst, or GRB. For a few brief seconds, this single dying star would outshine all the 100 billion stars in our galaxy combined. It would be a beacon of almost unimaginable power, a fleeting lighthouse visible from the edge of time. If we were to witness such an event from a safe distance, it would be the greatest firework in history. But if the Earth were to lie in the path of one of those jets, even from thousands of light years away, the consequences would be catastrophic. The burst of gamma and X-rays would slam into our atmosphere, destroying the ozone layer in a matter of seconds. The shield that protects all life from the sun's deadly ultraviolet radiation would be gone. It would trigger us a mass extinction event on a planetary scale. The sky would be filled with noxious chemical smogs, and the surface would be bathed in lethal radiation. Life on Earth would be scoured from the planet. We are fortunate that Stephenson 2-18's rotational axis is not pointed anywhere near us. The Stephenson 2 cluster would be irrevocably altered. The focused energy of the jets would act like a cosmic scalpel, slicing through the cluster, vaporizing any nearby objects and fundamentally reshaping the gravitational dynamics of the region. The hypernova explosion that follows, as the rest of the star is blown apart, is orders of magnitude more powerful than a standard supernova. It scatters a greater quantity of heavy elements, and scatters them farther and faster across the galaxy. It is creation and destruction on a scale that pushes the boundaries of physics and imagination. It is a fittingly operatic end for such a cosmic titan, a final, bellowing roar of defiance against the dying of the light. And yet, there is a third path, a possibility born from the star's extreme mass that is, in its own way, even more unsettling, a fate that is not a roar, but a whisper. What if, when the core collapses, the star is simply too massive for any explosion to escape? What if the gravitational pull of the newly formed black hole is so overwhelmingly powerful that the rebounding supernova shockwave, the very engine of the explosion, never gets started? The shockwave pushes out, but the gravity pulls in with even greater force. The explosion is smothered in its cradle. The outward blast is stalled, reversed, and swallowed. In this scenario, there is no grand flash of light, no supernova, no hypernova, no warning. The star simply vanishes. One moment, Stephenson 2-18 is there, a luminous giant star pouring light and heat into the cosmos. The next, it is gone. It would be the ultimate cosmic disappearing act, a quiet, insidious implosion, as the entire star, all of its 2 billion suns worth of volume, is consumed from within. The outer layers, which moments before stretched across our solar system, would fall unimpeded into the waiting maw of the central black hole. The light from the star's surface would be the last thing to escape. As the photosphere collapses inward at relativistic speeds, its light would be gravitationally redshifted into oblivion. The star would fade from view, not with a bang, but with a silent, drawn-out whimper. To any observer watching, it would look as if someone had reached out and turned off a cosmic light bulb. This is the theory of direct collapse, and it is perhaps the most profound fate of all. Because the object it leaves behind is not a typical stellar mass black hole of a few dozen solar masses, by swallowing the entire star whole, the resulting black hole would weigh in at hundreds, perhaps even 1,000 times the mass of our Sun. This would create an intermediate mass black hole, or IMBH. These objects are the great missing link in astrophysics. We see the small black holes left behind by normal massive stars, and we see the supermassive black holes millions or billions of times the Sun's mass that lurk at the centre of every galaxy, including our own. But we have struggled to find the ones in between. How do you get from a stellar black hole to a galactic behemoth? The direct collapse of a star like Stephenson 2-18 provides a stunningly elegant answer. These hypergiants could be the seeds of galactic monsters. Their quiet deaths could be the birth cries of the gravitational anchors around which entire galaxies will one day pivot. It's a chilling thought, that the largest stars might die without a sound, slipping out of existence and leaving behind an object of pure invisible gravity, a hidden titan waiting to grow. Whether its end is a brilliant supernova, a terrifying hypernova, or a ghostly silent collapse, the demise of Stephenson 2-18 is not truly an end. It is a transformation. It is a pivotal act in the great cosmic drama of creation, because locked within that titanic star is the future of the galaxy. The elements forged in its core, the carbon, the oxygen, the silicon, are released in the explosion. But the blast of a supernova or hypernova is an even more potent alchemical engine. In the searing heat and pressure of that final cataclysmic detonation, the heaviest elements in the universe are born. The neutron-rich environment allows for a process called rapid neutron capture, where atomic nuclei are bombarded with so many neutrons they become unstable, decaying into new, stable, and heavy elements. Every atom of gold in a wedding ring, every trace of platinum in a catalytic converter, every single nucleus of uranium that powers our cities or arms our weapons. None of these precious, heavy elements can be made in the normal life of a star. They are forged exclusively in the heart of these dying, explosive behemoths. Stephenson 2-18 is a cosmic treasure chest, and its death is the key that unlocks it, scattering this unimaginable wealth across the void. This process is called galactic enrichment. The star's final act is to seed the surrounding interstellar clouds with the raw materials for complexity. It provides the heavy elements necessary for the formation of rocky planets, for the building blocks of geology, chemistry, and ultimately biology. The iron that courses through your veins, the element that allows your blood to carry oxygen, was forged deep inside a massive star and flung across space in its death throe. The calcium that gives strength to your bones was created in the same cosmic furnace. We are, in the most literal and profound sense, the children of these cataclysms. Our bodies are built from the ashes of dead stars. When we look at Stephenson 2-18, we are not merely observing a distant exotic object. We are looking at a living example of one of our own cosmic ancestors. We are seeing the process that made our world and our very existence possible. And so the great cycle continues. The star's death will enrich the gas and dust of the Stephenson 2 cluster. From that enriched material, new stars will coalesce, smaller and more stable, perhaps. Around them, new planets will form, planets born with an inheritance of heavy elements that our own early solar system could only dream of. What kind of life might arise on such a world? What new possibilities are unlocked when a solar system is seeded with the complete contents of a hypergiant star? The legacy of Stephenson 2-18 will not be written in the light of its life, but in the countless worlds and suns born from its spectacular, universe-altering death. Its final, violent breath is the galaxy's promise of a richer, more complex future. And as we stand here, on our small protected world, looking out across the gulf of 16,000 years, we realize we're not just witnessing the potential end of a star. We're watching the beginning of countless new stories yet to be told. And so, our journey across 19,000 light-years comes to its final, breathtaking vista. We have returned from the edge of imagination, having stood in the shadow of a star that defies not only our sense of scale, but the very laws we once thought were ironclad. To gaze upon Stephenson 2-18, even through the lens of data and deduction, is to witness a cosmic impossibility made real. It is to feel the foundations of our celestial understanding tremble, not with the force of its gravity, but with the weight of its revelation. For this star is more than just a record holder. It is a profound and unsettling question, written in fire across the Milky Way. Our odyssey began where all great astronomical quests do, with a faint, almost insignificant glimmer. A whisper in the data, a point of light nearly lost within the crowded, dusty star-forming cradle of the Scutum-Centaurus arm. The Stephenson 2 cluster was a known stellar metropolis, but one of its residents was a recluse, shrouded in a thick veil of interstellar dust that absorbed its visible light, leaving only the faintest infrared signature to betray its presence. It was a cosmic phantom hiding in plain sight. Unravelling its true nature was an act of celestial archaeology, requiring us to sift through layers of cosmic dust and gas, to decode the subtle language of its spectrum, and to correct for the dimming effect of a journey that stretched across millennia. Each calculation, each refined measurement, was like a brushstroke on a hidden masterpiece, slowly revealing the contours of something truly monolithic. We traced the painstaking work of astronomers who, armed with increasingly powerful telescopes and sophisticated models, refused to accept the simple answer. They saw in that dim crimson glow a paradox. The star was too faint to be close, yet its temperature suggested it was a cool, dying ember. The only way to reconcile these conflicting clues was to accept a conclusion that bordered on the absurd, that the star was not small or dim at all. Instead, it was an object of almost unimaginable size and power, located at a staggering distance, its true glory almost entirely suffocated by the vast cosmic fog that lies between us. The moment of realization must have been one of sheer, unadulterated shock. A quiet gasp in an observatory control room, a number on a screen so far outside the expected range that it had to be checked and checked again. But the data held. The calculations were sound. The ghost in the machine was in fact a Titan. A star so colossal that if you were to place it at the heart of our own solar system, its fiery edge would engulf the orbit of Saturn. Every planet we know, from Mercury to Jupiter, would become nothing more than vaporized atoms within its churning, incandescent atmosphere. Our own Earth would be a memory, swallowed whole more than 1 billion kilometers deep inside this celestial furnace. For a moment, we must pause here. Let the sheer physical reality of that statement settle. This is not science fiction. This is not a theoretical construct. Stephenson 2-18 is a real place, a physical object, a sphere of plasma burning with the light of nearly 500,000 suns. It is an anchor in the cosmos, a gravitational gyroscope around which its smaller yet still enormous cluster mates faithfully orbit. To comprehend its existence is to fundamentally recalibrate our perception of what a star can be. For decades, we have operated with an understanding of stellar limits, a theoretical ceiling on mass and size governed by a delicate and violent balance. A star, after all, is a constant war fought between two implacable forces. There is the inward crush of gravity, relentlessly trying to collapse the star into a single point. And there is the outward blast of radiation pressure, the fury of nuclear fusion in its core pushing everything apart. This cosmic duel defines a star's life. If a star accumulates too much mass, the radiation pressure from its hyperactive core becomes so intense that it should, by all rights, blow its own outer layers away. This principle, known as the Eddington limit, was thought to be a hard boundary, a cosmic constitution that no star could violate. Then came Stephenson 2-18. It doesn't just break the rules, it dances on the very edge of them with terrifying grace. It exists in a state of such exquisite, violent equilibrium that our models struggle to contain it. The star is so massive and luminous that it lives its life on a knife's edge, constantly shedding enormous quantities of its own substance into space. Its stellar wind is not a gentle breeze but a celestial blowtorch, a torrent of charged particles carrying away the mass of our own sun every few 100,000 years. This process creates the vast layered nebulae we see around such hypergiants, the ghostly shrouds of their own self-destruction. This behemoth is, in a very real sense, dissolving itself, bleeding its essence into the void. Its very formation becomes a profound mystery, a challenge to our theories of stellar nurseries. How does a single protostellar cloud gather so much material in one place without the nascent star's own radiation pressure blasting the remaining gas and dust away before it can grow to such proportions? Did it form through a series of dramatic, chaotic mergers, with smaller stars colliding and coalescing in a gravitational mosh pit? Or does some unknown physical mechanism allow certain privileged stars to bypass the normal checks and balances, to gorge themselves on their birth cloud in a runaway process of accretion? Stephenson 218 offers no easy answers. It is a monument to our ignorance, a beautiful, burning testament to the fact that the universe is far more creative and far more extreme than our equations had ever dared to predict. And what of its final act? For a star that has lived such an extraordinary life, its death will be a spectacle of unimaginable proportions. The fate of stars this massive is one of the most exciting and debated topics in modern astrophysics. For many years, the default assumption was a hypernova, an explosion so cataclysmic it would outshine the entire Milky Way galaxy for a few brief, glorious weeks. A blast that would forge the heaviest elements in the universe, gold, platinum, uranium, and scatter them across light years of space, seeding the next generation of stars and planets. This is the cosmic alchemy that makes our own existence possible, the cycle of stellar death and rebirth that enriches the universe with the building blocks of life. But Stephenson 218's immense mass presents another, even more exotic possibility. It may be too massive to explode at all. The inward pull of its own gravity might be so overwhelmingly powerful that when its core finally runs out of fuel, there will be no outward explosion, no final defiant roar of light. There will only be silence, an instantaneous, unstoppable collapse. The star would simply vanish. Its entire substance, all 2 billion kilometers of it, would be crushed down into an infinitesimal point of infinite density, warping the fabric of space-time around it so severely that nothing, not even light, could escape. In a silent, non-violent implosion, one of the brightest objects in the galaxy would be snuffed out, leaving behind a stellar mass black hole of immense gravity. Which path will it take? The glorious, life-seeding violence of a hypernova, or the silent, space-time bending finality of a direct collapse? The answer could rewrite our understanding of how black holes are born, and how the universe is chemically enriched. Watching stars like Stephenson 218 is like watching a titan on a tightrope. We are witnessing the final, unstable, magnificent moments of its life, a performance that has been running for a few million short years, and whose finale is now, in cosmic terms, imminent. Within the next 100,000 years or so, a blink of an eye in the grand scheme of things, this star will meet its fate, and when it does, it will send a wave of information, either in the form of gravitational waves from its collapse or a flash of gamma rays from its explosion hurtling towards us. It is a message from the dead, already written, that will not reach Earth for another 19,000 years. A final postcard from the edge. This single point of light forces us to look forward, to ask the most fundamental question of all. What else is out there? Is Stephenson 218 truly the ultimate outlier, a 1 in a trillion cosmic freak? Or is it merely the largest star we have found so far? Lurking behind other, even denser veils of dust in our own galaxy, or hidden in the glare of distant galaxies, could there be stars that are larger still? Stars that push the Eddington limit not to its edge, but past it, operating under a physics we do not yet comprehend. The quest is already underway. With every new survey, we are cataloguing the heavens with ever greater precision. Instruments like the James Webb Space Telescope are designed for this very purpose, to pierce the dusty shrouds of stellar nurseries and galactic cores, to hunt for these hidden giants with its powerful infrared vision. Future ground-based observatories like the extremely large telescope With its mirror the size of a small building, we'll be able to dissect the starlight from these behemoths with unprecedented detail, analysing their atmospheres and mass loss rates to finally test our theories against their extreme reality. We are entering a new golden age of discovery, where our technological eyes are finally becoming sharp enough to resolve the universe's most profound secrets. The search is no longer just about finding bigger and bigger objects to claim a new record. It is about finding the breaking points in our own understanding. Each new discovery, each object that defies our neat categorization, is a gift. It tells us where our knowledge is incomplete. It points the way to new physics, new theories, new revelations about the inner workings of the cosmos. These extreme stars are the crucibles where our theories are tested, and often where they are found wanting. They are the engines of scientific progress, and in the end, perhaps that is the ultimate significance of this distant, impossibly large star. It reminds us of the sheer, humbling grandeur of the universe in which we are so infinitesimally small. To contemplate Stephenson 2-18 is to be confronted with a scale that our minds can barely contain, a power that dwarfs all human experience, and a beauty that is born from the most violent and extreme forces in nature. It connects us to the grand cosmic narrative. The iron in your blood, the calcium in your bones, the oxygen you are breathing at this very moment. These elements were not forged in the Big Bang. They were created, atom by atom, in the heart of a star that lived and died long before our sun was even born. Stars like Stephenson 2-18 in their final, explosive moments are the great sowers of the cosmos, the alchemical furnaces that create the raw materials for planets, for life, for us. We are, in the most literal sense, the children of the stars. Our existence is a legacy of their deaths. And so, when we look out into the darkness, we are not just observers of a disconnected, sterile cosmic machine. We are looking at our own origin story. We are seeing the process of creation unfold on the grandest possible scale. The universe is not just out there, it is in us. This realization transforms our perspective. The night sky is no longer a collection of distant twinkling lights, but a vast interconnected ecosystem, a tapestry of creation and destruction of which we are an intimate and inextricable part. The discovery of Stephenson 2-18 has not just given us a new sense of scale, it has deepened that profound connection. Our journey to this celestial leviathan has shown us that the universe will always be more spectacular, more mysterious, and more surprising than we can imagine. For every question we answer, a dozen more, deeper and more wonderful rise up to take its place. That is the true engine of human exploration. Not the finding of answers, but the relentless, insatiable pursuit of the next question. Stephenson 2-18 will one day fade, its brief, magnificent life ending in a flash of glory or a silent collapse. But the sense of awe it has inspired, the scientific curiosity it has ignited, and the humbling perspective it has given us will endure. It has left an indelible mark on our celestial map, a beacon reminding us that there are giants in the sky, and that our quest to understand them has only just begun. The cosmos awaits.